Have you ever tried breaking a chalk into smaller pieces? No matter how small you go, at some point you hit a limit. That's what early scientists thought atoms were. Indivisible. Dalton's atomic theory said atoms couldn't be broken down further. But then, the late 19th century changed everything. The discovery of the electron and proton revealed that atoms had internal structure. This overturned Dalton's idea of indivisibility. But now came a bigger challenge: how are these particles arranged within the atom? And to answer that, scientists began proposing atomic models, starting with the very first by J. Thomson. Imagine a Christmas pudding, soft, sweet, and studded with raisins. J. Thomson used this very analogy to describe the atom. He proposed that an atom was a sphere filled with positive charge, and within it, electrons were embedded like raisins in the pudding. Or think of a watermelon: the red pulp is positive charge, and the black seeds are the electrons. According to Thomson, the number of negative electrons exactly balanced the positive charge, making the atom electrically neutral. It was a simple and elegant idea for its time, but as experiments progressed, it fell short in explaining some critical observations, like the behavior of alpha particles. To dig deeper into atomic structure, Ernest Rutherford conducted a brilliant experiment. He took a thin sheet of gold foil, just 1,000 atoms thick, and bombarded it with alpha particles, heavy, fast moving, positively charged helium nuclei. What did he expect? Maybe small deflections. But what actually happened stunned him. Most alpha particles passed straight through. A few deflected, and a tiny number bounced back directly. In Rutherford's words, it was as shocking as firing a cannonball at tissue paper and having it rebound. This meant the atom was mostly empty space, but it had a dense, positively charged core. Rutherford pieced the puzzle together. His observations led to a new atomic model, the nuclear model. According to this, most of the atom is empty, and all the positive charge and nearly all the mass are concentrated in a tiny region at the center, the nucleus. The electrons, they revolve around this nucleus, much like planets orbit the sun. The size comparison is striking. The nucleus is about 100,000 times smaller than the atom, but there was a flaw. Physics tells us that revolving charge particles should lose energy and spiral inward. If that were true, electrons should crash into the nucleus and atoms should collapse. But atoms are stable. Clearly, a new idea was needed. To address this instability, Niels Bohr introduced a game-changing concept. He said, electrons don't revolve randomly. They move in fixed orbits or energy levels, which he called discrete shells. These are labeled as K, L, M, N, or N equals 1, 2, 3, 4. While in these orbits, electrons do not radiate energy. Only when they jump between levels do they emit or absorb energy. This explained atomic stability and even the hydrogen emission spectrum. Bohr's postulates blended classical physics with quantum ideas, giving us the first real sense of why atoms behave the way they do: stable, yet dynamic. There was still a missing piece. The atom's mass didn't add up if you only counted protons and electrons. Enter James Chadwick. In 1932, he discovered the neutron, a subatomic particle with no charge but a mass almost equal to that of a proton. Neutrons are found in the nucleus, along with protons. They add mass without adding charge and help stabilize the nucleus by reducing electrostatic repulsion between protons. Except for hydrogen, all atoms have both protons and neutrons in their nucleus. The total atomic mass equals the sum of protons and neutrons, the two heavyweights of the atom.